Okay, welcome back everybody. I want to jump gears and jump into the EM algorithm. I want to point out also the book does invariance of the MLA before the EM algorithm, but I want to spend a little bit of time on the EM algorithm. Invariance of the MLA, we'll give a proof for this later. This is always true. Let me just tell you what this part of the book says. This might be the easiest proof in the book. I probably said that like 3 or 4 times, so there's some ties. So this is a contender for it. It says this: if I have a likelihood function, I'll write it out like that. X is fine, I've been using that. And I come up with the arg maximizer of theta. That's theta hat. That's the MLE. So I'll call it theta hat MLE. Just to be specific, that's a specific type of estimator. I didn't say how we got this. I didn't say we did calculus to do it or ran an algorithm to do it or something like that. I just said we have it. So theta hat. So this could potentially be a really hard problem. High dimensional spaces, lots of multimodality. But let's say we've got the maximizer. I call it that. And somebody says, I don't like thinking about theta. I like thinking about a transformation of theta. So somebody else likes to think about tau theta. So that's a function of theta. If I were a Bayesian or something like that, and that were a random variable, it would be a transformation of that random variable. But for an MLE, I haven't necessarily said that it's a random variable. So it's just a function. I haven't induced any properties to say that it's an actual random variable. So slight difference. So I put a function of theta right here. And I want to know, and I'm going to call this maybe psi. So I'll just give it a new name. And maybe we want to know psi hat MLE. This is really easy to do. Does anybody know what the answer is?
Yeah, you just how
That's it. That's always true. No matter what tau was.
should tau be like a 1-to-1
What did I just say? So, did I say that it should be 1-to-1?
it should be
Everything. This is always true. So, there's a proof in the book that it's very easy to show 1-to-1. So, because you can actually write down really clearly what the inverse map is. But it doesn't have to be 1-to-1. We just have to change what we mean when we invert. So, just like all this stuff, pseudo inverses, lots of different types of inverses, you got to pick a point out of that whole thing. But it doesn't matter which point you pick. So, it can map back to many things and it won't make any difference. So, always true. So, just make a note. Does not need to be 1-to-1. So it's always true. That's what it says. So see if you can follow that proof, and understand what it's actually saying. I'll show you an example after we get through EM and make sure that we understand what a proof looks like. Any questions about that? At least it's a pretty neat thing. If I got the MLE to some problem, I can get the MLE to other problems. So it could be easier to get maximize on theta space and just plug it into the function than maximize on tau theta space. So that could happen. So we could look at some examples of that. But sometimes working under some transformations are just easier mathematically. Cool.
question.
Yes.
So what about, let's say, you are looking at theta values, possible theta values from negative infinity to infinity, and your function is an absolute value. Are you still going to lose something?
No, that's fine. It'll work. It's just going to absolute those things out. This is true always.
So how are you going to know if you're
I'm not mapping back the other way. You took the absolute value and you're the one that ripped off the sign, and it'll be the right answer. So you're thinking about the inverse map, but I don't need the inverse map to do this. I just need the function. So I don't even need to solve for the inverse map. That might be part of the proof, is to show what happens in the inverse map. But I'm not inverse mapping anything, so it just works out. Yeah, still always true. It's as easy as it looks. So, you know, it could be something like this. This could be sine to the arc tangent, I'll say e to the tan, inverse tan theta. So something that you know is not anything, and I can even do that, absolute value if you like. So that's a function that I can take. I can take any logs or anything and do anything crazy. Nope, that's going to be a function. So it can be as bizarre as I want. So if I've got theta half, somebody told me what it is, I just plug that thing in, and that's going to be the MLE for that. So it really is that simple. A lot of the midterm and final questions coming up are going to be like that. To make sure you know how to use this result. But I might say, do a maximum, find it. Now find me the maximum under this other thing. And if you're aware of this result, boom, you just write it down. Or you spend 20 minutes doing a new maximization problem. So I'll make sure you understand what this means and not just do the proof. I'm always enamored when people can do the proof and then you ask them to do the little example and they're not quite sure how the pieces fit together. Okay. Anyway, I told you how the pieces fit together. We'll do the proof later. That's true for any sort of maximization problem that you're even playing around with. That's kind of a cool thing. There's nothing special about it being a likelihood. Okay. Let's motivate EM with a problem that we're going to come back to. So I can fill in some notation. I'm going to give you the EM algorithm in general this time. We're going to do the proof in general, and then we'll fit all the pieces together in the example. But I want to give you the example first. We're going to iterate. So finite mixture models. This is these sort of models are a place where a lot of people use something EM or EMS. You know, there's a lot of things that people use with these kind of older algorithms, and there's modern incarnations of them. And to the old guys, it's really all the same, isn't it? We just rename the names on everything. So I'll tell you a little bit more about that after we get through this. So finite mixture models. And I'm thinking about the additive type of mixture models. So there's scale mixture models where I integrate over the scale parameters. So I'm just going to be playing around and mixing over the location parameters. Those are additive models. They look like this. So I'm going to have some random variable, xi, some instance, and it's going to be distributed according to a sum. And that's the additive part. Cap k, that's a number, and that's finite. That's the finite bit of it. I'm going to have some weights on each component of the model, and I'm going to have some probability distribution. Fx given theta k. So these are going to be model parameters. For the k model component. There's a restriction on our weights, their probabilities. The pi k's have to be greater than 0, and they have to sum to 1. Where I sum over all the things. This is a probability distribution, so I'm imagining this is maybe some density function or probability function. I'll talk about it in terms of a density, but it could be a mass function as well. So density or mass. And so one thing to notice is that if that's a density function, if I integrate over x, that all sums to this thing as 1. And when I average over that thing, This is all going to sum up to 1. So this is a probability distribution. So if I integrate over x, this whole thing sums up to 1 because those sum up to 1. And so that's a probability distribution. And that's kind of a cool probability distribution because there's a lot of flexibility. So it's definitely multimodal by design. So if f of x given theta k looked like this, 1 over 2 pi square root sigma k e to the minus 1/2 x minus mu k squared sigma k squared, we would call this a Gaussian additive finite mixture model. So theta k's here are the model parameters mu k and sigma k. So a lot of the theory that we've already learned extends to properties about this model. So, but of course, estimating the parameters in this model might be very difficult. So let me tell you more about that. If this is true, then we have a finite Gaussian mixture model. So that might look like this. So if I've got cap k is equal to 3, you might have mu1 here, mu2 here, mu3. I've got some densities over the top. Something like that. So these weights right here are controlling the heights of this distribution. So we have to control the areas under there because we want this all to add up to 1. So this is just a superposition of these Gaussians weighted by these pi's right here. So I'm just kind of stacking them on top of each other. So that's all we're doing. So that's a Gaussian mixture model. There's going to be different variances in here, sigma 1, sigma 2, sigma 3, controlling the widths of all of that. These are very flexible models. I would say probably about half of our colloquium speakers have played around with models like this. I like playing around with models like this. I don't always like talking about the population average. So I could probably say a lot of things if I had something like this, some distribution would look like this. I had data that came from it. So I have a histogram representation of this. Something like that. I could maybe say, well, I could look at the overall X bar of this. And this has finite variance, this model. There's finite variance in all of those components. So there's finite total variance. So CLT can kick in, and I can talk about the global average. And the global average, let me maybe change my example, make that a 4, just so that I can be a little bit choosy about this. And say there's this other mode over here, and I can talk about X bars like over here for all of the groups. So, and I can say, oh yeah, and it's normally distributed, and I could be talking about the average, and I could be making perfect mathematical sense. There is some average over there, but it pertains to no individual out there. So if I were doing something like personalized medicine, I would hope this wouldn't be the case right here, that they're trying to target on average some prescription that deals with all the groups, and they're a little bit worried about them, and they're a little bit worried about these guys over here, so they come up with a prescription that's suboptimal for everybody. But on average, it works great. So I hope that's not what my pharma company and my doctors are doing. Although, I know the truth. So this is probably a little bit more devious than what you might see in reality, but it makes the point. So I can still talk about X bars normally distributed, build up a normal distribution, figure out what that average is. Question is does it matter? And personally, what I would like is somebody, if the data looked like this, not to talk about global X bar, but to talk about the group means and tell us what they all mean. And hopefully somebody could come in and identify what these different subgroups are. So, and tell us what is controlling their variability. Does this match up to certain groups that are obvious in the population? What's going on here? And so, when I watch the news and they tell me about things like flu rates across the country, I just kind of don't care. So I care a little bit, but I want to know what's going on around me and around areas like me. I don't really care what's happening in LA. So because LA's epidemiological behavior is totally different than Blacksburg. So I don't know if I'm making an actual specific point about anything. So if LA shuts down, do we need to? So anyway, I think that what we need to do is kind of stratify and group things and make decisions based off of those actual groups. Politicians feel differently about these things. So anyway, I'm going to give you a simulation study and not actually the context of stuff where you're going to simulate some data and then you're going to run the EM algorithm and you're going to learn what all these different means and variances are. And I'm going to ask you to do that in one-dimensional and multi-dimensional space as well. So at least two-dimensional space. If you want to crank it up to 20-dimensional space, you can. You're going to need a lot of data to figure out what the groups are. So that will be something you'll figure out in your simulation study, and I think that makes sense. So another name for all of this is clustering. So some people call it that. So this is a model-based cluster. Cool. Let me just talk about real quickly how I would sample from this model. So if I'm going to sample from this distribution right here, there would be two steps involved. I've got to deal with which component I'm actually in. So I'll just kind of map out, this is the probability of being, and I'm going to write it with English and then I'll give us some notation later. Being in group K. And so I could call this something different. I could maybe call this class K. I could call it maybe cluster K. I could call this component K. All synonyms for each other. So a lot of people just use different words for the exact same thing. I often talk about class. Okay, I don't know why I like that word. I just like it for no other reason than that's probably what I call it the first time. If you want to think about it as clusters or groups, go ahead. So there's going to be two steps to this. So I'll butter up the notation. I don't have the class labels buried in this, and that's intentional. But what I would first do is I would sample which group I'm in. So I would take a multinomial draw with pi 1 to pi k, half k in here. So this is just a k-sided coin flip. And these are the probabilities of landing on a certain side. So maybe I should call it like a k-sided die. So maybe you're thinking about one of those Dungeons and Dragons dies, so that you can pick up. So I'm going to give this a little bit of notation right here. I'm going to say Ci. So I'm going to do this iteratively. I goes from 1 to n, where n is going to be my collection of data. Right here, I'm just going to draw that from a multinomial. So I'm going to just impose some new notation, just to keep track of what I'm doing. So what I did is I flipped the coin with that probability to identify which component I'm in. So if it lands on the third side, it means that I'm in that component, right there. So I flip the coin. If it lands on the first side, I'm on that component. So pretty simple. And then the second thing we do is we draw xi's from that component. F of x given theta, and I'm just going to write this down. Ci right here is going to be my label. Or I could change this a little bit, and I could say this is k, and give us a little bit more notation and say Ci is equal to K. I like it like that. So the reason I like it like that is a condition on all the things that I know. So it follows my pattern. So you might accuse me right now of getting ready to be a Bayesian. And sometimes I say, that's not correct, that's not why I do it. It actually helps me to be a Bayesian in this case. So I'm going to make a point about that a little bit later that the book doesn't make. And I'd say probably about 80% of papers written on EM talk about everything is through the Bayesian lens, but not everybody does. So everybody get this? Flip a coin, pick your component, and then sample maybe the continuous thing, the normal thing. And I think that's exactly what that says right here. So that's what that means. So I'm going to be in the components with the relative frequencies proportional to these, because I'm flipping the coin like that. It's going to land on those components with that relative probability, and then I'm going to be sampling from the right thing. It's going to have the right structure. So this is how you do it. Okay. What we might want to do so probably a goal would be to infer the model parameters. Bless you. So goal, we want to learn mu k, sigma k. We want to do all of those. I'll say k goes from 1 to cap k. So I want the collection of these standard deviations and means, or I can think about this if I wanted to. Same thing, you tell me sigma, I tell you sigma squared. And we also want to know these pi k's. So we want estimates for all of these things. So I need the pi k's, the weights themselves, and I need model parameters. For any mixture model, this is what you would need to do. I'm going to just make a comment. You don't always have to stick with the same distribution right here in an additive mixture model. I could have combinations of different distributions. So one thing I like to do is I love using Gaussian mixture models because they're pretty smooth. They're smooth, they're nice, so I can kind of make any distribution out of them. So that might sound familiar to the signal processors in here, that they can kind of model any signal using sines and cosines. So their basis function for modeling signals is sines and cosines. My basis function for modeling weird probability distributions is Gaussian inference. So same sort of concept. Question in that?
I was actually going to ask something along those exact lines of how useful would it be to use this to approximate some arbitrary distribution and then use it to sample from it. Like maybe could it be an alternative to using like Metropolis Hastings for some high-dimensional?
Possible. Yeah, they would be competitors. So I could estimate this whole model using Metropolis Hastings. They would be similar in some of the ways that the algorithm works. EM is going to give me MLE estimates for all of that stuff. Metropolis Hastings would give me the full joint probability distribution of all that stuff. And so Metropolis Hastings would give me a larger answer. Now, very often, it's a very good question, what I'll do if I want to speed up my Metropolis Hastings stuff is I'll run EM in advance and I'll have really good starting locations for everything. What do I do in advance of that? I run k-means to seed my EM and get that thing figured out. So I'll just point out k-means is just like this, it's approximating this, but the constraint on k-means is that all the sigmas are the same. So k-means would be estimating that. So we just make it a note. If you're familiar with this, if you're not, go home, read the Wikipedia page and go, oh, I get it. So it is like this. So k-means assumes the sigmas are all equal to each other. K-means doesn't assume anything. The person that invokes the algorithm, that uses it to do the estimation, might inadvertently be assuming this. I've been editing some grad student work later, and I tell them algorithms don't assume anything. So people assume things. So be careful when you're writing, but I'm going to give myself a little bit of room. Just be loose about this. So K-means assumes all of that. If I used maybe Mahalanovitz distance or something like that for doing K-means, hopefully it converges to an answer that's similar to this, what we would get out of EM. So you can change the distance functions as well. So I might do something like that, run K-means, throw it into EM so it runs lightning fast, get a good answer out of EM that's a little bit more refined, throw it to my MCMC, and it gives me something as fast as possible. So a lot of times in MCMC, just getting it to burn in is the, in a high dimensional space where you've got a lot of interactions between parameters, getting it to burn in is the hard part. So speeding it up and giving yourself good initializers is important. If you're a theoretician, don't worry about any of that. So, but if you're actually going to use these algorithms, it's important. Okay, I'm just going to kind of point out, just as a heads up, very often all we get to observe are these xi's. So you get to see the xi's, I get to see the histogram. I might be able to eyeball what cap k is, so I'm sliding that under the rug right now. I'm just assuming you know what cap k is. For your homework assignment, you're going to get to know what cap k is because you're going to simulate from it. So you're going to run a for loop where you simulate from that. You know what the model structure is, and you're going to try to relearn the model parameters. If you don't know what cap k is, there's a number of things you can do. So I could fit lots of different models with different cap k's, and then I could look at the overall likelihood function from this and look at which one has the higher likelihood for the different varying k's after the model, after we converge and I have my MLA estimates. And I plug them back in. And I can draw a plot of what that likelihood function looks like. And so hopefully that plot doesn't look like a straight line, as I vary k over it. So I could look at something like this, the likelihood, and I could look at possible values for cap k, and I could look for a plot. If you'd like, I could look at the log likelihood. I think that's more common, what people look at, and that'll look like this, maybe, something like that. The likelihood would go the other way. So hopefully it looks like this. Bam. And you'd say, k's there, so I'm not getting any great, any better answer if I keep increasing k. So very often you'd like to impose a penalty on this so that you could decide that's the right point. But a lot of people will do this without the penalty, and they'll just kind of look right there. This is called a spree plot. So just write that down. Spree plot. I like to call them elbow plots. So I think that's the way I heard about it first. So you're looking for the elbow. In real data, I see this all the time. It's a lot bendier. So I got to pick somewhere. Pick that. So it's hard to say. So hopefully it doesn't make a big difference in what you're doing. So I would pick different k's, show what your different answer is, and describe the variation of your answers for things you don't know. There's another thing you could do. I could pick different k's and I could average over those k's. So I could average those models over the various k's and come up with solutions. That's a little bit tricky to think about, but if I were doing predictive modeling, that's something people do quite often. So that's, if I were to name it, I would call it Bayesian model averaging, where I average over lots of different models. What would be my averaging weights? They would probably be the posterior probabilities for those various k's. So I'd have to put a prior on k and try to learn what k is. There are some early attempts at doing that where people maybe use a Poisson distribution. What else would I use? It's some counting thing. So, but that's highly parametric, and parametric assumptions might be driving some of your inferences, and people don't like to deal with that. So there's newer versions of doing this, something called Dirichlet processes. gives you a probability distribution over k without building in such a hard parametric constraint like the Poisson. And I'm not going to tell you exactly what that looks like, but if you guys want a review session and ask me about it, I'm happy to go on for hours. So, but I'm not going to test you on that. So there's stuff other professors in the future will tell you about. So this is just one stepping stone in that direction. Okay. So for everything in this class, we know cap K. You get to know it. If you don't know it, you have to do something else. So maybe build your screen job. If you want a little fancier, come back and see me and I'll tell you what a Dirichlet process is. Okay. Oh, I'll also just make one more mention. If you ever hear anybody talk about variational inference, variational Bayesian inference, it really is an approximate model that you're fitting using EM. That's all that's happening. So you have this approximation. It's called a fully factorized approximation. I'm not going to talk exactly about it. There are other incarnations of it. It's not the only one going, but it's the one that most people use. And then you fit EM to find a solution to that approximate model. There's lots of fancy ways to talk about it through a measured theoretic lens. But at the end of the day, it's just EM on an approximate model. Okay. So you can be thinking about that in talks where people talk about variational inference. You can go, well, it's something like EM. Very much like EM. Okay, let me tell you what EM is. If it's not obvious, we're going to use EM to solve this thing. Let me just say one more thing about this before I jump into EM. Let me just say, if you knew what the C's were, this problem is easy. So, if you knew the CIs, I'll call it cap C, C1 up to CK, i.e. the class labels, then inference is easy. Let's just see. On the homework assignment, the simulation study concerning EM, I'm going to have you derive stuff that's similar to this, so you're going to do some MLE calculations and tell me what the MLEs are. But let's just imagine this in one-dimensional space. The homework will take you up to higher dimensional spaces. If you'd like to think about two-dimensional spaces, that's fine. So you can derive everything that way and do grad school induction. That would work. Inference is at least presumed easy if I know what the C's are. Let me just ask this. How would you get this? Mu1 cap.
What would you X bar conditional on CI equals 1?
Yeah, so let me say that a little bit different. I would just average the XI's when CI is equal to 1. And I take that average. So what I might do is just look at the XI's right here. And I might do something like delta function CI is equal to 1. So where that just lights that up to a 1 or a 0. That's just an indicator. So it's going to be a 1 if CI is equal to 1. Otherwise, not just averaging over everything. If you'd like to be smarter about this, there is a denominator right here. I haven't written it down yet. If you'd like to be smarter about this and subset out those x's so you're not adding a bunch of zeros, that'd probably be more efficient computationally. So, and then I'm going to just divide by, I'll say the sum of the indicators, CI is equal to 1. So this is just going to be the number of elements where CI is equal to 1, and the top is just the XI. So this is just the X bar constrained to the CIs where everything was 1. So I go from 1 to n. That's one way of writing it. How would you come up with the pi case? Pi 1. exactly. So just the relative frequency. So this would just be some of the indicators, maybe Ci is equal to 1 divided by n. So that's that proportion. So I'm just making up notation as I go. Having the Ci's makes this way easier. So building in some notation for it. So I'll kind of point out right here, this is really just the probability that Ci is equal to k. So that's what that thing is. And I might be a little bit more superfluous and say this is C is equal to K in here. So just to change my notation is a little bit. What's this? Sigma 1, I'll make it squared. What would you do for that?
Just look at the S estimator, but conditioning on CI.
So I just look at something and then it's done.
Well,
What's the formula?
oh, right.
I know what you're going to say.
Right. So the sum over the xi's minus x bar conditioned at all squared. And then that thing squared, and then conditioned on Ci is equal to 1 and over n minus 1. Oh,
And?
over,
Right.
the sum of the things where it's equal to 1 again.
And you said minus 1?
I want to say minus
Anybody have any other answers?
Depends on which estimator you want to use.
Which estimator do you want to use?
Plus
Plus 1. So maybe plus 1. Maybe not. We're so indoctrinated, aren't we? We just want to say minus 1. That staff on the home teacher just can't get away from this. So they crunch you in your brain as well. I would probably use that one. But this is the maximizer in this case. So this would be the MLE, and this is the one you would encode with EM. So would be the answer because it's the MLE. And so if we're maximizing, we're getting maximum. So in the context of the algorithm, this is the one we use. Of course, we don't know these, so we're going to have to be learning these things as well. Okay. So those are all the MLEs. I'll just point out. You're going to derive those in high-dimensional space, but your intuition is on. So typical MLE type estimators.
So pretty much if you handed us data and now you said like which data point this distribution was sound.
Yeah.
Super duper easy.
Super easy. So at current iteration of the algorithm, here's what it looks like conceptually. You're going to try to figure out a probability for those CIs. So I'm going to have my 4 different things right here. It's some iteration of the algorithm. I'm going to have a mu1, a mu2, a mu3, a mu4. That's what this represents right here. I'm going to have some weights for it. Maybe this hasn't converged yet. If this is trying to estimate what I've seen from the previous picture and I've sampled, the algorithm hasn't quite converged yet. But maybe I'm getting some semblance of convergence that it's kicking this thing out. So at some iteration, I'm going to look at an xi. So that's an actual data point, and I'm going to ask, which distribution do I think this came from? And so just looking at the picture, you'd say that one right there. If xi was here, which distribution do you think it came from? This is a little bit more challenging. You might say that's about 50-50. But low probability it came from that, and low probability that it came from that. If I looked at something like this, let's say I had some split right here. Let's say this looked like this. This is the bisector right there. That's what I'm imagining, those 2 things. So if my xi came from something that looked like this, which model do you think it came from? Let's call this 1 and let's call this 2. Probably 2. Why? More variability. Exactly. This is the thing that will break k-means. So if you have like something like this in higher dimensional space. Let's see, that's the bisector. I've got some circle like this, and I've got some data point xi. This would be in high dimensional space. You can see in this picture, it probably didn't come from that distribution. It probably came from this one. So the variability has to be accounted for as well. David?
When you draw it out, you just look at which line is higher, right?
Yeah, that's the way that I draw it out. But I would probably be doing a probability calculation. So what I'd be doing is taking all of these different densities right here with my current state of affairs, plugging it into that, and plugging the data point into that and seeing which one is higher. So that's where the MCMC and EM kind of differ in how they deal with that. They both are thinking about that as a probability, or at least I'll say 90% of EM members think of that as a probability. I'll say a little bit more about that later, but in Maze you're explicit about it. Let me tell you what the algorithm is. So let's just adjust our notation to just being general. And then we'll recirculate after we're through this algorithm, the general thing, and we'll match it up to everything in this finite mixture model. So I'm going to step away from that for a moment. So here's the goal of the algorithm. It's to maximize something. I'm going to say maximize f theta. A lot of books don't write in the data, but I'm just going to write this in and make my notation conditional on data so we feel like we're statisticians doing all of this. So this algorithm can be used for any parametric model where you're trying to maximize this, but I want us to just think about us as statisticians so I can give you some context. Maybe that's a likelihood function. So, and we're going to arc maximize this. I'll also say maximize this over theta. That's the goal. And this is going to be equal to the maximization of theta integral. And I'm just going to give us some different notation. Normally I wouldn't change this between little f and cap f, but I just want to be able to distinguish these things. So cap f is our goal, so we'll capitalize it. This is going to be theta, same thetas. And then there's going to be some missing something in here. So this is missing. So there's some notation that people will use for this. I'm going to integrate over psi right here. So the goal is to maximize some function where there's some missing part to it. And what we're going to do with the missing stuff is a little bit different than the thing that we're trying to learn in the first place, the theta. We're going to average over it. And so this is the sticking point. This is the contentious part for a lot of people. This is the opportunity for an argument. So I'm treating the two different things very differently. So one I average and then one I maximize. So I would say the averaging steps looks and feels a lot like what a Bayesian might do. So if this was a likelihood function right here, you're integrating over it, I would say, wait a minute, didn't you use some prior on everything? So you had to have done that to upgrade it to a random variable. And if you went to a hardcore frequented school, that's when they'll kick me off. So no, just integrate over it. You're allowed to do it. And I'd say it needs to be a random variable. Like what's the measure in the space? Like I don't get what we're doing. So I'm going to assume you have a flat product in there. I think that's what you do have to do. Be consistent about probability rules, but not everybody likes that lingo. So there are other ways of talking about this, but I want to just point out we've integrated over something. It kind of looks and feels like what a Bayesian would do, and then we maximize over something. But looks and feels like maybe other people do. So I kind of see this as a compromise. If you're going to try to be risk adverse about something, you want to average over it. So this is just a good idea. So average over the missing component. Just don't plug in your best guess for it. Try to deal with its uncertainty. So the lingo that a lot of people will use, so call this the complete likelihood. And this is the incomplete likelihood. Just keep these terms in mind so when you hear people talk about them, you know what they are.
Do you mean the f on the inside is the complete or the everything?
Yes. Otherwise, I would have used the same term for two things. So, yeah, it's just a little bit of lingo. So size, just here's some examples. In general, this could be missing data. So this could actually be like X's that are missing from parts of the thing. So there could be some entries in there, I just don't see it. I could call that missing. What am I gonna do with that? I'm gonna average over it somehow. So I have to have some weights on what I'm averaging over. It could be random effects and different groupings. See people apply this quite often on random effect models, which are really just clustering models. I'll just point out. Or maybe this is class labels. So this sort of stuff is what I'm thinking about. So the labels, the CIs in our mixture model. So that's going to be the connection that we're going to make. That's going to be the missingness in our thing that you get the XIs, but you don't get to see the Cs. So the lingo that we might use is that that's a latent variable. It exists, it was there, but we never got an opportunity to see it. So anything latent or missing. They're synonyms. Let me tell you what the algorithm is to accomplish this goal. I want to point out there's two steps going on here. There's an integration and a maximization. So there's an averaging and a maximization. There's an expectation in a maximization happening. So, and that's where we get the name of this algorithm. This stands for expectation. And this is maximization. So we see two steps that look like that in the actual problem we want to solve. So here's the algorithm. It's two steps. And next time when we come in, we'll prove that this algorithm accomplishes this goal. It's not obvious. Maybe it's obvious to somebody, but it wouldn't have been obvious to me a long time ago without doing the actual proof. Looks like this. So what I'm going to do is I'm going to iterate over some large number of iterations. Big. It's got to converge. How can I tell what big is if the algorithm is still moving and the estimates are moving around and not converging to something I haven't converged yet? It's not big enough yet. So same thing, we needed to check for any iterative algorithm, something needed to be accomplished, i.e. we needed to converge to a solution. So step one, this is called the E step. There's going to be a step two, this is called M step. This is going to look like this. You're going to build this function, we're going to call it Q. I'm going back to my general notation, theta. So I've got some thetas I'm wanting to learn. In my Gaussian mixture model, that's the means and the variances and the pies and everything. Those are the model parameters I want to learn. And I'm going to have some iterative form. So I'm going to connect this to some previously learned theta. So we need to initialize for our 0th step. First thing we need to do is initialize. I'll say theta 0 to something. Q is this function. It's going to be the expectation of the logarithm of the joint distribution. So this is going to be theta and psi given d with respect to psi given theta t. So let me just tell you what this expectation actually is that you need to solve. This is the integral of the logarithm of, I'll say, joint theta and psi given d. And this is going to be integrated with respect to this distribution right here. This is psi given theta t, and I'll write it d right here, d psi. So if you'd like me to put in the d right there. Everything's conditional on the data. If you ever lose track of the data at one step of your algorithm, you've made this gross here. So everything and get to know what the data is. So this is just some integral that we need to solve. And then what we do in step 2, this is the easy part, is we're just going to be maximizing this function. Q theta given theta t. I'm going to look at the arg maximizer over theta, and this is going to update theta t plus 1. So there's just 2 functions right here, and I need to demonstrate to you that this algorithm actually solves this problem. And there's all kinds of weird stuff going on right here. So I'm not even working with quite the correct function, I'm taking a logarithm of it, or at least something like it. Remember, our objective is this. Logarithms shouldn't bother us. It's just a monotonic transform, and it's not going to shift our optimas around. But then I'm taking this expectation and I'm connecting it to something else. So that's kind of weird. So it's not obvious that maximizing this function is maximizing this function. That's what we need to prove. So maximizing that function in step 1 is the same thing as maximizing this once that converges. I'm going to point out real quickly, for the homework problem, you can write this down in closed form. So you're not actually updating the expectation every step. In here, you're not solving a new integral, you're just updating it with some placeholder, your last thing. So in the finite mixture model, Gaussian thing, you're going to have a closed form for that. You don't need to solve an integral on every step. You just need to know what that integral is. And that's what I'm going to ask you to work through on the first part of that problem. I'm actually going to tell you what the answers are and tell you what you need to code up. So it turns out coding this up is relatively easy as long as you write down the Q correctly. So you're just maximizing over some Q function. I'll point out a couple things. This doesn't need to be exact. This could be a Monte Carlo approximation. And this maximization doesn't need to be exact. It just needs to be increasing. So one thing we know about maximization, if I keep increasing, I'll eventually hit the top of the hill. That's a basic principle, bless you. If you're ever up hiking and you look to the top of the hill and you're thinking, how do I get to the top? The answer is keep walking. So keep moving up in some direction. If you just keep moving up one step in front of the other, you will eventually hit the top of the hill. That's also a metaphor for graduate school. So in the rest of this semester. So let's just keep marching. We'll circle back around to this, and I'll try to explain why this algorithm converges to that, and then I'm going to wrap it up and bring it back to the context of the finite mixture example. And then we'll go back and vary from the end. Thanks a lot, you guys. That's it for now. It does. Close enough. Anyway, welcome back everybody. I want to go over the lecture that I tried to give you a video to. I tried to watch it myself for 15 minutes. And I thought, this is really hard to do. So I think we've all learned our lesson that being in class is a good thing. Also, I like to keep those 2 days in reserve for if I do get sick. So we've used one to kind of catch up, and we got another one. So apologies, because I know you probably watched the video and all of that. I'll see if there's another day we can give up, but I don't think so at this point. So I'm going to try to just keep everything on pace from here on out. But I think we're in good shape, but you never know. We might get a day off. Again, if I get really sick, I'll take a day off. I'll try to make myself come to class. So. Okay, let's go through the algorithm. So I want to just point to the problem we're going to study, the finite mixture model. We'll do it in the Gaussian case. The finite part is that you know what cap k is, or at least you can infer it somehow, but every time you run the model and you do the inference, it's with a finite cap k. There are other algorithms where you don't know what cap k is and you put a probability distribution on there. So if you're Bayesian, you can do that with a parametric prior or a non-parametric prior. So there are different ways to do it that we won't go into, but I think you get the idea. this is a stepping stone towards those more full-blown analyses. Of course, it's really hard if you do MCMC or something, and you put a prior on K because you have the dimensionality of the model changing all the time. So there's lots of little issues that if you don't know K, what you do. There are ways of handling it. It would take me another week of lecture to even get through, so we're going to hold off on that. EM is a popular algorithm for maximizing stuff. So what we're going to try to maximize in this example is we're going to try and come up with MLE estimates of all of these parameters right here, and then that right there. That's the probability of being in group K. I can call it cluster K, component K, lots of different names for the exact same thing. I want to just point out, this really is the probability that Ci is equal to K, where Ci is an indicator on the group that you're in. So there's this auxiliary variable, you might call it a latent variable or something that's missing from your observation. All you're going to get from this, so I is going to go from 1 to n, you're going to get a histogram of data. And it's going to look like something that's clustered, where all the components are normally distributed. So we're maybe thinking something like this. But the heights of those, the number of samples, is relative to the probability of being in that. So the goal that we're going to be looking at is trying to estimate this model. I'll try to match it to the notation here that's a little bit more general. What we're going to be doing is we're going to be averaging over the C's in all of this. So I'll try to allude to that when we're running through the proof, and then we'll circle back around and show how to use this algorithm and come up with the stuff that you're actually going to encode on an upcoming simulation study. So to generate samples from this model, we're first going to flip a coin, multi-dimensional coin with these probabilities right here, pi 1 through pi k. All of the pi's sum up to 1. Since I'm calling those a probability, they're necessarily positive. So these are positive. They're bounded between 0 and 1. So this is our goal. This is the missing stuff. Alan asked a question and said, are there any restrictions on when you can use EM? Just as long as you can write down the likelihood correctly for everything. So what you might be thinking about is what is the likelihood for this model? So we need to write down the likelihood using the C's, and we're going to need to average over those. That's the E step right here. And then we're going to need to maximize over the parameters of interest. Those are the pi's, the mu k, and the sigma k. I'll just give you a heads up. The pi k's are pretty obvious how you estimate them. So it's some iteration of the algorithm. The MLE estimate is the frequency of the number of samples that you believe are in that group. So the other MLEs that we're going to get, and I'm going to ask you to derive those, are just weighted averages for representing the mu's. So using the relative pi's for the xi's that are actually in the different components. I've drawn you a picture of this, but I think we do actually need another 20 minutes just to talk about what all those details are. So we're going to circle back around to this, but I want to go general first. So here's the algorithm. The goal is to maximize something. So you might want the maximum of this. Generally, I want the argument that maximizes it, the thetas. So in our case, the thetas here are just the mu1s, or I'll say the mu k's, and the sigma k's, and the pi k's. And if you like thinking of sigma squared k, we can write it down that way. And you've got a whole bunch of these. So k goes from 1 to cap k. So that's my thetas in this. The missing stuff right in here, this part is missing. So in our actual model over here, these are the C's. So that's C1 to Cn. If I gave you the C's for everything, everything's really simple. So you would just average over those xi's in that component if you knew them with certainty, you just average over them and just come up with the groups of X bar, and then you would have the empirical forms for the sigmas. So I'll point out that you don't actually subtract off 1 in the sigmas. The MLE is divided by the number of elements in those groups. So we'll derive those. This is a maximization problem with a constraint, so you might be thinking about Lagrange multipliers. So I might give you a little mini example there. I'm going to ask you to fill in all those maximizations, but maybe I'll take you through an example or two and leave one of them for you. Okay, proof time. So this is what we want to prove. So we want to maximize this. I want the maximum likelihood estimates of all those parameters in the model, but I need to average out the missing stuff. So I'm going to average over the C's in our case. So this seems like a good idea. Things that I don't know, average over them. I'll just say that's a winning idea anywhere you are. So you're uncertain about things, average over it. What does averaging do? It reduces variability. So if you're just thinking about normality, when you average, instead of having a standard error of sigma, we have a standard error of sigma over root n. So it drives down the variability of things. I might say you might want to come up with average estimates of theta as well, but sometimes you want just the best estimate. So the full-blown Bayesian implementation of this would be coming up with averages for theta and psi. So I want to just point to one of these steps looks eerily Bayesian to me. This isn't a full-blown philosophy class, but we can insert some of it. That how am I integrating over something if it's not a random variable? So if that doesn't bother you, no big deal. It doesn't bother probably millions of people out there. So you can fall into that camp. We're going to talk about that step a little bit later. What I'm kind of imagining is maybe this is a likelihood function right here, and that's why I'm plugging in D. If you look at a lot of books, they won't plug in D in condition on the data all the way through. I like thinking about the data in every one of my steps because I'm a statistician. But this algorithm could be generalized to any function, really. It doesn't have to be a data-dependent function. There's 2 steps involved. First step is the E step. It's an expectation. So instead of maximizing over that function explicitly, we're going to maximize over something that's kind of like it. So this E step is the expectation of the log of that joint right here. That integral looks like that. So what we've done is we've introduced this new object that's going to be iterated over at every step. So what we're actually doing, instead of trying to solve this big global problem, is we're trying to break it up into a sequence of small maximization problems. And if you've ever seen like steepest descent or conjugate gradient, they're doing the same sort of thing. So what they're doing is they're maximizing these sub-maximization problems that eventually converges to the maximum of that. So the idea is that as we keep maximizing over this function right here, eventually these things right here will converge to whatever this answer is. So we will call this theta hat. So the idea is that as I get this sequence of theta t's, t goes from 1 to cap t, as that thing gets big, this sequence is going to converge to that. So just like any maximization problem. Okay, so Zach said, oh yeah, he looked at the algorithm and said, this is obvious, that this thing converges. There is some insight. I don't know if it's obvious that it converges, but I sympathize with that because there is some insight that you could use to say, this looks like it could converge right here. I'm maximizing over theta right here. That theta has the same meaning here, so at least I'm thinking I'm doing some maximization in the same direction as the maximization that I'm trying to solve. And I'm averaging over this stuff right here, and I've averaged over it over here as well. So I'm kind of using the same operations on things, but I've also introduced this into everything. And I'll point out that maximizing that is not identical to maximizing this at every step, yet, but it does converge to the right thing. So it's a little bit different. The logs probably don't bother you because that's just a monotonic thing. So that doesn't mess us up. So what I'd like to do is prove that this right here converges to the sequence of these. So we'll prove that star is solved by the EM algorithm. How do I prove that? So Dayquil makes me a little bit unlike myself. Okay, I'll be there. I think I got it. Okay, so here's my proof. Note f theta. I'm just going to rewrite this function. This is our objective, so let's think about this for a little while. I'm going to rewrite this as, let me write it a little bit different. This will probably help us. I'll write down that f sine given theta and d is equal to the joint model theta, psi, and d divided by kappa f. That might not be super obvious, but let me just rewrite that. It says that f theta given d is equal to, I would say this is pretty obvious right here. So this is just a joint divided by its margin gives me the conditional. So I've kind of done something that looks like a probability rule, and that's how I'm thinking about it, but you could apply that to a likelihood function, and the same thing would happen. So we teach this in probability class, so if you want to think about these as probability functions, that's kind of how I think about them. The only place that they're off is by a prior sitting there on theta. So we haven't included that, and the algorithm doesn't do that because it's maximizing theta. I will point out there is an implicit prior on psi, but I'm a Bayesian and I can't help but think about it that way. So if you think that you can just integrate over your parameters, your model parameters in a likelihood function, we're pretty close to each other, and I don't think that there's anything to fight about. So, but I would say, I'm going to assume you have some prior in mind. So I'm going to assume that you've imposed a flat prior. I won't accuse you of it because I don't want to get into an argument about what I believe you think, because I really don't know. Okay, so f theta is just f, the joint, divided by the conditional. So, pretty straightforward. I'm going to take the logarithm of both sides. Log f theta given d is equal to the logarithm of the joint minus the logarithm of the conditional. I think all of us would agree that maximizing that would be equivalent to our original problem. And so usually it's an easy thing to do if you live in the exponential family. Taking a logarithm just turns your function into something that looks a little bit more linear or quadratic. So in the case of the Gaussian, it just turns it into a quadratic, which is an easier maximization to do. So I haven't perturbed the problem any. I just wrote it down a little bit differently. Now I'm going to take an expectation. I'm going to take that same expectation we're looking at right here. So that expectation means that I'm integrating with respect to this right here. So again, I'm going to average out the missing stuff. A really good idea. If you don't know what it is, average over it. So what we're going to get is expectation psi with respect to this thing. That's going to be what we're iterating over in our algorithm. logarithm f theta given d. I'm going to conclude and take the expectation over these two things as well. So minus another expectation. I'll finish filling this out in a second, but I want us to just focus on the left-hand side. Did I perturb it in any such way that I've changed the dynamics of the problem? And if I maximize over this, I get a different solution than what I'm looking for? Or is it the exact same thing? Because this is about what we're going to be looking at right here. Not quite exactly. So I'll just point out, I haven't done anything to this problem right here. If I maximize that, f, that is the solution to the problem that I'm looking for. If I take a logarithm, that's the solution to the problem I'm looking for. If I maximize it, obviously I've stretched the space, but it's preserved where the optima are. And when I take this expectation, I'm taking an expectation over psi, and there's no psi's in here. They've already been integrated out. So the expectation of psi with respect to that is just this thing. It hasn't changed anything. There's no psi. So if I integrate over that, and that's a proper distribution, the integral over the psi is conditional on the theta t's is just 1, and I can factorize this part out. So I haven't changed this problem as well. What I have changed is the stuff on the right-hand side. So this is going to be the joint log f theta psi given d. This is going to be psi given theta t. And this is the log of the conditional. Psi conditional on theta and d. Okay, I'll point out this looks familiar to us, this first term. The second term doesn't. Somebody tell me, where does that first term appear on the board? I've already written this term down. It's right there. This is q, right here. So this is the q function. I'll write it down like this. That's q, that's the notation we used before. And this is some other function. I'm going to call it s. So it turns out EM isn't maximizing that thing explicitly, it's maximizing a chunk of it. I'm going to break this thing, aren't I? So I'm not maximizing f, I'm maximizing a bit of f. And I'm forgetting about all of this. And the question is that fair game? So it's fair game if no matter what I do to this function, this always decreases. So what we're going to do in our proof is show that this is a decreasing function. It's always a decreasing function no matter what we do with it. So, and that's what we'll prove. So if I'm subtracting off something that's always decreasing no matter what I do to it, then this part doesn't matter. It's always just getting smaller and smaller and smaller. If that was a plus sign, this would be a problem. But since it's a negative sign and I'm just subtracting it out, subtracting off something that's just decreasing, then it's fair game. So I will point out that on our next iteration, we actually do something explicit. I use knowledge about Q to do it. So I'm not going to prove exactly how I pick that theta t plus 1 decreases this. What we're going to prove is this is always decreasing, no matter what. So we're going to prove this. S theta star given theta t is going to be less than or equal to S theta t theta t. So no matter what this is. So this is only equal when that thing is theta t. And any other value I plug in there is going to decrease the function. It's going to bring it down. So that's kind of cool, and that's why we get to throw it away and not think about it. That's the part that's not obvious to me. When I see two different functions and they're not the same, how can maximizing one be the solution to the other? And it's true of all the other stuff that I'm just forgetting about is decreasing the function and I'm subtracting that off. That's also leading to a maximization. So this actually accelerates things to forget about this. Let's prove that. To myself on how to prove this. I gotta get the first step right. Okay, so proof S given theta t is decreasing. Okay, let me just write this down. Integral f psi given theta. I'm going to plug t plus 1 in here. This is the part I always forget. Do I plug t in there or do I plug t plus 1 in there? T plus 1 is probably the easier way to do it. If you do it the other way, it works out as well. So d psi, I think I know what this is. So all of my integrals that I'm writing down are definite integrals. So I'm integrating over the entire space of psi. So again, I'm thinking of this as a probability model. So what does that integrate to? 1. So that's 1. So that means that the logarithm of this f psi given theta t plus 1 and d psi, that's equal to 0. Now I can do some other stuff. I can apply Jensen's inequality to this. So this is an increasing or a decreasing function? It's strictly one thing or the other. It's increasing. So it slowly increases after a while. So this is an increasing function, and I can apply Jensen's. So Jensen says something about this, and there's some relationship. We'll have to figure out which way this goes. With the integral of the logarithm of this thing. Psi, actually, let me just change a little bit more. I'm going to do this step in just a second. Let me just rewrite this ever so slightly. I'm going to write this f psi over theta t, and the data times f psi given theta t, and the data d psi. So I haven't changed anything. I just multiplied by a funny version of 1. Okay, there's some relationship with this function. Integral logarithm of this ratio, f psi, given theta t plus 1, and d, f psi, given theta t, and d. Close that up, integrate it with respect to the same function. V psi. So the question is which way does this sign go? So is it this way, or is it that way? We know it's not equal. The only time it's equal is if that is a linear function, and that's not linear. So this is a case where Jensen's applies. So again, let's do our trick real quick. We learned this maybe in a review session a couple weeks back. Here's what I always do, is I can't forget this is greater or equal to 0. So let's just a memory trick. So that's variance. That's how I know that's greater than 0, but I also know what that function looks like. So I've got expectation of x squared is going to be greater or equal to expectation of x all squared. And I also remember what that thing looks like. It looks like that, a parabola. So when the function looks like that, the sign goes that way. When the function looks like that, the sign goes the other way. So which way does this go? This one or this one? Here's 1, here's 2. Let's do both. 1. I've got 1, 2, 1, 2, 3, 4, 5, 6, 7. Colby, not willing to commit yet, right? It's too early. We got 8 right here.
Still reading.
Hines isn't convinced.
I'm still reading, so I can't skip it.
Okay, fair enough, fair enough. Too busy reading. Some of us are waking up. Some of us don't feel well. So, which way does this go? Are we
That way.
What's that?
I'm flipping sides, I think.
You want to go that way?
To 1.
You want to go that way?
Yeah.
You want to go this way?
Yeah.
This is the correct answer. So, just keep in mind the way I flip this right here is my transform is on the other side. So the way that I've done this. So this is this way. My function is on the outside is that one right here. So I have the 2 parts of the equation spun around. So it could go the other way. So anyway, I think it's this way. So good job. Mike, that was you. Nicely done. So your 9 a.m. brain works great. So that's the part I always mess up. I cannot get an inequality correctly, and I can't do basic algebra, but for some reason I can do calculus. So, okay, that's the direction. Now we just need to play around with this part a little bit. So this part is just the integral of the log of f psi given theta t plus 1 in d. F psi given theta t in d minus, so I'm just taking that and I'm writing this out as the difference of 2 things and then writing it, it's 2 integrals. So integral f logarithm of f psi given theta t d times f psi given theta t d psi. And this was d psi in here as well. So I can recognize what this term is. And I have 2 different versions of the s term. I apologize for writing that down. That was over here in your notes. But this looks like s again. S is the logarithm of the conditionals, where q is the logarithm of the joints. So that's what q was. So this is s right here. Where were the arguments in this? This is s. This is that first argument right here. This is theta t plus 1. Given theta t, so if I just want to see where my placeholders were, that's that right there. So that's not integral. I'll make this look like an s. Minus another s function. Again, this is an integral sign. This is my s that we wrote down before. This is going to be theta t given theta t. So that's that argument right there, and this one pertains to that slide. So easy to get confused. You have to just remember what the placeholders actually mean. And we already know that this thing is less than or equal to 0. That's the far left hand of this. And so I think we've proven what we have to prove. So I'm just going to rewrite this again. Theta t, given theta t, this is going to be greater or equal to s theta t plus 1, given theta t. So it's not even considering how I got the theta t plus 1. So I didn't even use that in the proof, how we actually obtain theta t plus 1. What we're just saying is that no matter what we do, we're going to decrease it. So this function looks like this. I have a theta t. Any other value that I plug in is going to bring this thing down. So that's what's going on with this function. That's what it looks like. So that's why we can ignore it. And I'm subtracting that thing off. So I'm always subtracting off something that's getting smaller and smaller and smaller. So we can ignore it. So that's the conclusion of the proof. It's just this Jensen part that says we can ignore s. It's decreasing. So hopefully you understand that connection. If not, go back through all the steps and try to remember that. There's a good chance I'm going to test you on this and ask you to remember this proof. So my experience is that nobody really understands this algorithm by doing the proof or by doing the example. It's only when you put them both together and keep iterating and looking back and forth at the two different things, the theory and the application, that you start to understand this algorithm. Okay. Is it hot in here? Let's go to our finite mixture model and see how to apply all this stuff. And I'll spend a little bit more time next time talking about these steps, and I've got a version of this coded up, so I'll run it for you. And then I'll tell you a little bit more about the simulation study and what I expect. Don't worry, it's a little bit easier than our other simulation study because we're not comparing 3 techniques. We're just going to see how well one technique works. I'll write down Gaussian mixture. This doesn't have to be Gaussian. This could be any sort of mixture components, and you can even mix and match them. It will, of course, change what you do in your maximization step or your averaging step. So you do have to solve this integral up front. I'll kind of point out that if you've got a closed form solution for Q and that closed form solution doesn't change, you don't need to solve an integral over and over and over again. So you don't actually need that expectation to be exact. You need it to be approximately close enough. So you can use a Monte Carlo estimate in there. That's what people will call Monte Carlo EM. It's when they don't know how to actually write down Q in closed form. So in your example, in our example here, you're going to be able to write down Q in closed form, and so it's just iterating over the maximums. If you can solve what those maximums look like in closed form, it's just an iterative update. And so it's actually a really simple thing to code up, just so long as you do the math up front reasonably well. So this is kind of the downside to the algorithm, is you do have to solve an integral before you do anything else. So finite mixture model. So we've got, I'll say, xi's are coming from some model, I'll call it P of x, given theta, and I'll write this out a little bit more explicitly. This is k goes from 1 to cat k. Pi k, those are our mixture weights, times some normal. UK sigma k. So again, that's our model right there. And I'm going to have n of these. I goes from 1 to n. So again, when we simulated this, we had to introduce this auxiliary variable c. So we knew which component we were in so that we could sample from that correct component. I'm going to write down the likelihood function. Question. Some people call this the complete likelihood. It's the part that includes all the missing stuff. So I'm going to encode this with the actual C's and be thinking about these C's when I write down the likelihood function. So this looks like this. That's the easy part. Everything is conditionally independent. So if I know all the model parameters, all things are conditionally independent, I can just represent this with a product. I'm going to plug in my mixture model. Everybody stop writing for a second. I'm going to write the wrong thing down first. And we can just think about the wrong thing for a second. I'm just going to write this down right here. Pi k. And this is going to be my normal xi mu k sigma k. What's wrong with this?
You have to have, because each group A, you have to have include the I relationship inside that.
Yeah, you need something to tell me which group I'm in. The problem with this is, when I'm writing it down this way, is I'm plugging xi into every component right here. So I'm plugging it into all of these different normals, and that's wrong. Xi only came from one of the normals. It didn't come from all of them. I'm not averaging over that. It came from exactly one of them. So this expresses that it came from all of them, and that's not how we generated it. We flipped a coin, and then we generated the x from one normal component, not all of them simultaneously. So this isn't right. So what I need to do is I need to rewrite this down normal xi. Again, this is going to be a PDF. What I'm imagining, we'll re-encode it with the actual p to the f, e to the minus quadratic form. But that's going to be a PDF right here. Given, I'm going to write it down this way. Mu k, sigma k, and I'm going to be specific that ci right here is equal to k. So I'm going to write that last part down right here to indicate which component I came from, and then I'm going to add an indicator function in here and say ci is equal to k. So that's a 1 or a 0. It's one of those things. So if I knew what the ci was, I could turn that on and off, which thing it came from, and then I can think about this sum a little bit differently. So let me just ask you a question. How many non-zero things are in that sum? There's only one. So there's really only one normal density sitting right in here. So all the other things have been multiplied by 0 and they're gone. So there's only one term in this, and I'm zeroing everything out with that in its additive form. So I kind of like writing it down like this. So I really like writing it down like that right there, conditional on C, because I can think about how I update that to a random variable. So I'm going to write it down that way, and I think that's actually helpful. So this conditional information lets you know all the stuff that you know in the problem. I've kind of made a mistake right here, and I need to be thinking about this maybe a little bit differently. So I'm not going to butter up the notation yet, but I want to remind myself right here, I get to know theta t. So at the previous iteration of the algorithm, I get to know what those thetas are. So I'm conditioning on that. So when I actually do the integration and I'm integrating out the c, I'm integrating with respect to c given theta t. So that was the expectation we took. So keep in mind, all our expectations, they look like this. Expectation psi given theta t. That was the expectation that I was taking of the log joint. So this psi was c right here, and I got to know what theta t is. So in our case, we get to know what all our previous values were, our mu's, and our sigmas, and our pi's from the last step. I also want to remind us, we actually get to know the data as well. I didn't write this into everything, but at every step we get to know what the data is. We never have to forget that. And so I get to know the data as well. I'll just kind of point that out. Let me just ask a question. For each data point, if I knew what all the mu's and the sigmas were, for each CI, how many of the x's do I need to know? Let me just draw you a picture real quick. Imagine this is my current state. I'm just kind of imagining cap k is equal to 3 right here. So this might be my current knowledge of mu1. So that might be a t on there. This is mu2 t. This is mu3 t. Okay, so that's my current state of knowledge of what this distribution is. I also have corresponding sigmas in here. So sigma 1t, sigma 2t, sigma 3t. So, do I need to know all of the data points right here to try to guess where maybe xi came from? So for each xi, each one of these, if I knew what that was, do I have enough information on the board to try to answer which component this xi came from? Or do I need x2, x3, x4, all the other xi's? Let's imagine this is x1.
You need all that.
You only need the one. So if I know what all of the other model parameters are, everything is conditionally independent of each other. So given a state of thetas, that's all I need to know to try to guess which component the xi came from. So probably this mode right here, but I can't totally exclude that. And I can't quite say that's a 0. Numerically, it might be pretty close to 0 right here, because this looks pretty far away. So, but there's some probability, and that's what we're actually going to be looking at, is what are those probabilities, and we're going to use that in the algorithm. We'll come back and we'll focus on this term a little bit more, but I want to just remind you to get to know all these things when you're trying to ask this question. So what do I do with all of this? Eventually, I'm going to take an expectation, I'm going to take a log over this, and then I'm going to take an expectation. I'm going to try to integrate out those C's. So let's just rewrite this a little bit more. So I'm going to rewrite this like this. I goes from 1 to n. I'll say sum pi k. K goes from 1 to cap k. This is going to look like 1 over 2 pi square root sigma k e to the minus 1/2 xi minus mu k squared over sigma k squared times this indicator function. Ci is equal to k. Again, I'll try and come up with notation when I take the expectation that I get to know things when I try to address this indicator function. We actually haven't used that information yet. That's where that expectation comes from, conditioning on theta t. I can get rid of that right there. All the 2 pi's are common, but I can't throw that thing away because we don't know what it is. So I'm going to rewrite this just a little bit differently. So I'm going to rewrite this like this. Pi 1 to n. And just bear with me for a second. I'm going to write this in multiplicative form and not additive form. So I have everything written down in additive form. Here's how you write it down in multiplicative form. So I'm going to write e to the minus 1/2. I'll write it like this. Minus 1/2. I usually mess up the placement of this 1/2, so keep your eye on that. I've got these 2 terms that I need to include. So I'm going to include these into the exponent. So that's pretty easy to do. So this is going to be plus log pi k minus log sigma k. Now I'm going to close that brace. I want to be really clear, this is inside the brace right here. I'm just dropping my indicator function in upstairs. Oftentimes I get a question about this. Is how did I do that? How did I use algebra to do that? I didn't use any algebra to do that. I just thought about it. In fact, I didn't even think about it. I just read the books long enough that it did all the thinking for me, and now I just do this automatically. So I didn't use any special algebra to do this. I just shoved the indicator into the exponent. Let's think about what this does in here. When that's a 0, it turns everything upstairs into a 0. E to the minus 0 is a 1. So instead of adding zeros in additive form, all I'm doing with the indicator is I'm multiplying in ones. So how many components are in this part right here? There's really just still one. So if I just analyze this form right here, and I look at the indicator where one of them is 1, I just get one term that looks like this. The same exact thing happens here. So this just requires some inspection, just to see that they're exactly the same. When that's 0, it turns that all into 0, and it turns this multiplicative form into a 1. So this is just some fancy rearrangement. This is the hardest part of the EM algorithm, is figuring out how to rewrite everything so that the math is easy. So what we'll do next time is we'll come back through and we'll examine this expectation term right here. So I'm just going to take this right here, and what we're going to do next time is we're going to take this expectation, and I'm going to be taking this expectation with respect to C, given all of my current state of information. I get the D, which are really just the X's, but as we just saw from our picture, for each CI, I just need one XI to tell me what it is, and that's because I get to know what the betas are. Keep in mind, we're learning the betas through all of the X's. Then once I know a current state of the thetas, I only need one X to tell me what one C is. So I'm going to take this expectation and I'm going to drag it over this. What we're going to do first is we're going to drag that stuff up into the exponent. So I can write this thing instead of like this, I can write it with a double sum here. I'm going to take a logarithm of the whole thing, so then I'm just going to have this term up in the exponent. And then when I drag my expectation over it, the only place the expectation operates is on this last bit. So what we're going to wind up with next time that we'll look at, we're going to look at this equation. Double sum, I goes from 1 to n, k goes from 1 to cat k. This is going to be a minus 1/2. I told you I always mess that up. That minus only went next to the first term. Minus 1/2 xi minus mu k, sigma k squared, plus log pi k minus log sigma k times this indicator function, ci is equal to k. So that's what my log likelihood looks like. Then when I take the expectation over this thing, if the expectation is going to be operating on the ci, all we need to know is one of the x's to do this, and the current state of that. The only place the ci appears is right here. So this expectation is going to slide over all of this junk, and it's going to appear right there. And you can ask yourself, what is the expectation of an indicator? What is it?
Expectation of the sum of two. It's probability.
It's the probability of that event. So the expectation of the indicator of an event is the probability of that event. So how can you think about that a little bit easier through a Bernoulli example? So the expectation of a Bernoulli is the probability. Same thing happens here. They're not exactly all the same probabilities. So that's what we're going to work on next time when we come in, and I'm going to ask us lots of questions of how do I turn that into a probability. Probability of an event doesn't that have to be a random variable, and then I'm just going to drop it and say, of course this is Bayes' theorem right here. You'll still hear people argue about it, but I'm going to throw it out there and then I'm going to, I hope. Okay. Next time we'll come in, finish this up, I'll tell you the equations that you need to code up on your simulation study, and I'll walk you through that a little bit, and I'll give you a version of this algorithm so we can see how it performs, and we'll talk about issues that you should encounter. That's it for now, you guys. Thank you for your patience.